talking about random processes. And let's look at this lower left part of this slide again. And we're going to be talking mostly continuous signals. Say each one of these is a signal, right? In, in a random process, you have an infinite number of possible signals. Think of the whole signal as a realization. Any particular signal, a realization of that random process. And when we take averages, it's over all possible realizations. We're going to do it at particular slices of time. That's why, again, you can kind of think of a random process as having two variables. One is time, and the other is realizations. Let's cover some definitions that deal with random processes. First, let's say you have two random processes, an X and a Y process, X process and a Y process. You could have a joint PDF of certain X slices of time and certain Y slices of time. You call those two processes independent if this relationship is true. Any combination of X's and Y's and time slices for each one. That it breaks up into a product of joint PDFs just of X stuff times a joint PDF of just the Y stuff. Look at this and say, how would I ever prove that? We're really not going to do that. Its independence is often something we might assume, but we'll rarely prove it because you have to prove it for all these possible infinite number of permutations of joint PDFs. That's what it means for two processes to be independent. Another definition is stationarity, or strict stationarity. And it means this: for any joint PDF of slices of time, remember, each slice of time is another random variable. The random process is a sequence of random variables. If I just shift all the time arguments by the same tau, and it's the same PDF, or joint PDF, then you call that stationary, strict sense stationary. Fallout of that, for example, at any moment or any time is the same constant for all time, all t's. So again, it's hard to prove something's strictly stationary. It might be easy to prove it's not stationary if you could just show that any moment is a function of time. It's not a constant. Then you've proved that it's not stationary. Ergodicity is kind of a subtle concept. It means time averaging is equivalent to ensemble averaging. Remember, ensemble averaging is the way we do it. We do it over all possible realizations. It's just a subtlety. I won't get into it. And again, we'll generally just assume it where we need it. The autocorrelation function. This is that second order statistic I was talking about. I don't know if I did it in this video. We're going to satisfy ourselves with first and second order statistics. First order statistic is going to be the mean at every sample of time, and they could all be the same, or they could be a function of time. The second order statistic is this autocorrelation function. So this is a big deal because it's one of two big things we'll use to sort of characterize a random process. And here's what it means. Here's the notation, R for autocorrelation for something. of the random process X. Take two different slices of time, take this expectation. Remember, each one of these is a random variable. And what does that mean? We remember what an expectation was? Here's a function of two random variables. We put that function here, weight it with the joint PDF, and integrate it over all possible random variables. There's an equivalent for discrete time. We're going to be doing almost entirely continuous time stuff. So again, you have there's an infinite number of possible realizations. That's how we do our averaging over this conceptually infinite number of realizations at two different slices of time. And then take this autocorrelation function. That's what we're doing. Now we've got a new definition. We call it wide sense stationary as opposed to strict sense stationary. It's wide sense stationary if two things are true. One is the mean is just a constant for all t. Or you could say, if I had a capital T, I'm going to get the same thing. Or it means your mean is not a function of time. It's a constant over all t. Other thing to be wide sense stationary is the autocorrelation function. If I shift the arguments by the same t shift, then this is true. The autocorrelation function is the same for itself in a time-shifted version. The fallout of that is that the autocorrelation function, instead of being explicitly a function of two slices of time, it's just a function of the difference between the difference in time. And it'll turn out later, it doesn't matter if it's a positive shift or a negative shift. That is just a function of how far apart the two slices in time are. So now we can prove wide sense stationary. We just have to prove these two things, that the mean is not a function of time and that the autocorrelation function is only a function of the time difference, not the absolute time values. All those definitions, here's the Venn diagram. Be wide sense stationary, not necessarily stationary or ergodic. But if it's ergodic, it is stationary. And if it's stationary, it is wide sense stationary. So here's what I was saying. You can prove wide sense stationarity. Proving strict sense of stationarity, you'd have to look at all possible joint PDFs and all their combinations and permutations. But with wide sense stationary, you just need to show two things. Mean's a constant. Autocorrelation function is just a function of time difference. Got the mean. Here's how you calculate the mean, right? You already knew how to do that. We're doing this for a particular t. Why don't we just calculate the mean like we did for a random variable? Autocorrelation function, this calculation now. So in general, include processes that are not wide sense stationary. You have this. The mean square, if I use the same time slice for each of these, t and t instead of t1 and t2, that gives me my mean square value. So I can find the mean square from the autocorrelation function. If it is wide sense stationary, then the mean square value is just where the time difference is 0. 2 time slices at the same time. So in either case, I can find the mean square value from the autocorrelation function. And I think I'll save some examples for another video.